In 2021, I interviewed for a software engineering job at Google. I ended up getting the job, but I'd be lying if I said I wasn't anxious through the entire process. I had no idea what to expect coming into the technical interviews. Sure, there is some info around the web, like study LeetCode medium problems and focus on graphs, but all of that is generic and common advice. You've heard all of that before. If you're like me and suffer from imposter syndrome, then you want to know exactly what types of data structure and algorithm problems you can expect. That's why today I'm going to tell you about one of the literal interview problems that I was asked in my Google technical interview rounds. We'll walk through the actual problem the interviewer asked me, and not some similar problem on LeetCode. This will be the real deal. Throughout this walkthrough, not only will we explore the problem itself, but I'll give you all of the tips and tricks you need if you really want to impress on your interviews. This will be all of the tactics I wish someone told me before I walked into that Google interview. We have a lot to break down, so let's jump right into the problem. So this problem has a bit of a story around it, revolving around chemistry. Luckily, you don't need to know any chemistry to solve this one. One of our inputs for this problem is going to be a compound, which is really just a string. So let's say my input compound was NeCO. We're also going to be given a few different elements. Think of elements on the periodic table, just like you learned in chemistry class. So we have some elements, for example, O, OS, BE, N, and so on. What I want to do here is decide whether or not it's possible to create the compound from the given elements. In this problem, we can also reuse elements as many times as we need. So for this particular example, using NeCO as my compound, one way I could make it is to do the Ne plus the C plus the O. That would spell out NeCO. So that would be a correct result here. In this particular example, there are actually a few different ways that you could create the compound NeCO. You could do the Ne plus the CO directly. In either case, this would be a true example. In other words, it is possible to create the compound from the given elements. It just happens to be the case that there are multiple ways here. Let's look at another example. Let's say that our compound was NeRCO, and we were given the same elements. This would be an example where we should return false. It's not possible to create NeRCO from the given elements here. You'll notice that here I have an R within my compound string, and there's no way to get an R from the elements. So that's some quick intuition we can use to understand the result for that particular example. Overall, we're looking for a Boolean result, right? So true or false for this one. Let's take a look at another example, talking about that logic here. Let's say I had the compound SIR, right? It just spells out sir. I was given just a few elements. Let's say I was given Si, IR, and then also I. Let's take a closer look at this example because I think it reveals something important. If you wanted to try to create the compound SIR, your first choice will probably be to take the element Si. But from that point, you actually hit a dead end, right? Now that I take Si, the only remaining character to match up would be the R, but there's no R to be found in my elements. We do have an IR, but that won't be good enough, right? Because we already matched the I. So this is most certainly an example where we should return false. At first glance, something that might intimidate you about this problem is that it has a story around it. This is somewhat common for many FANG interview problems. What I mean is, this problem has a story about chemistry around it. When you receive a problem with a narrative like this, don't freak out. Don't worry, you don't need to know any chemistry to solve this one. What you need to do is cut through the noise and focus on the underlying data structure. In other words, this is not a chemistry problem about combining elements into compounds. It's really a programming problem about concatenating some strings together. The first step to attacking an interview problem is to frame it in common algorithm terms. And be sure to verbalize this out loud. So in my Google interview, I literally said, so what we really have to do here is to check if some target string can be constructed by combining together some smaller strings. As soon as I said this, I can see the look of relief on my interviewer's face. This simple statement establishes that the interviewer and I speak the same language, the language of programming. I call this first step labeling the problem. What I did was label the problem as a string problem. This is a critical first step because labeling the problem allows us to narrow the pool of potential algorithms we can use to solve it. For example, when you're given a problem about cities connected by roads, you should label that problem as a graph problem. Labeling a problem is about categorizing it into one of the common interview topics. So labels are things like string, binary tree, graph, dynamic programming, etc. Some labels are more specific than others. For example, string is a pretty broad label. Within string, there are more specific labels like two-pointer or dynamic programming. It's okay to start broad for now. We can narrow things further later on. The important thing is to start classifying what type of problem that we have. And be sure to verbalize it out loud. You need to use your interviewer to your advantage. What I mean is, if you label the problem correctly, then you'll get some confirmation from the interviewer. They might agree by saying right or sounds good. Sometimes it'll be more subtle. They might just nod their head and smile. Although subtle, this is still an invaluable signal. It'll give you the confidence that you're on the right track. On the other hand, if you mislabel the problem, maybe it's a linked list problem, but you mislabel it as a graph problem, then you'll still get feedback from the interviewer. They'll disagree with you and provide some counterexamples. This is still a good thing, so don't worry. When you mislabel a problem, you learn that your initial choice was wrong. Naturally, this helps move your focus toward the correct option. You don't fail an interview if you need a little push toward the correct solution. In fact, I think responding well to an interviewer's hints is a very good showing. It shows that you're collaborative and you can totally work with people. Remember that this interviewer is viewing you as a potential coworker, so co-work. The worst mistake you can make is to not label the problem at all. When you don't label the problem out loud, you don't give the interviewer the chance to set you on the right track. You might unknowingly go down a road that does not solve the problem. You'll waste time going for a flawed strategy. By the time you and your interviewer know what's happening, it's too late to correct and finish the problem within the time. Each of my Google algorithm rounds was about 40 minutes, and I'll probably be similar for you. It's not a lot of time, so this means that every minute is valuable. Labeling the problem out loud can save you precious time in the long run, so be sure to do it. Now, let's look at some more test cases on the whiteboard. All right, so we already stepped through some examples, but I'm going to give myself just a larger example that we can trace through fully on the whiteboard. Let's say that my compound is this string, HOCli, and I have these options as my chemical elements. I'll just go ahead and tell you that the result for this one is true, right? There's at least one way that you can build HOCli. One example would be like this. Cool. So we know that ultimately we're looking for a way to return true, but I want to break down that logic into an algorithm. Right? So how can you come up with the intuition for this problem? Well, the first thing I would sense here is I have multiple inputs to this problem. And generally, if I have a smaller input, that would be an easier problem, right? In this particular case, that would mean if I reduce the input size, that would lead to me solving the problem. I think recursion is a great strategy to use here, because of course recursion is where we take some larger problem and break it down into smaller instances of the same problem, until the problem size is so trivial that we automatically know the result. So what do I mean over here? Let's look at the two inputs to this problem, right? This is something that I see students struggle with sometimes whenever they want to write recursion. If there are multiple inputs to a problem, they aren't certain which of the inputs that they should shrink, right? Which one should actually reduce in the problem size. So our two options are either taking the compound that we have to target or reducing the size of the list of elements that we can choose from. So if we do some reasoning out here, the correct choice would be to actually shrink the target compound. And here's what I know. Let's say that you actually had a smaller segment of the target compound. Let's say that someone was just asking me, instead of finding if I can create Hockley, what if they just asked me to find Lee, right? Just Li. Well, if I was just trying to figure out if it's possible to create Li, the answer would be pretty trivially true, because Li is directly an element in my choices here. So that tells me that I think we're going to start by shrinking the target compound. Another giveaway here is the fact that they tell us in the problem that we can reuse elements as many times as we need. So you can't really shrink your list of elements in the first place. You can only shrink your target compound. So that's going to be a really important aspect of this problem, right? So initially I have this top level problem of trying to figure out whether or not it's possible to create the compound Hockley. Right? So I'm going to write that string within this node here, because I'm going to visualize my recursion using a recursion tree. It helps me really lay out the logic. All right, so now that I'm evaluating this problem, how can I break it down further? Well, what I want to do is, of course, match up some elements from my options here. So if I'm given Hockley, what I'll do is just target characters starting at the beginning of my compound here. So I can look at this H, right? H is definitely going to match up at the very start of my compound. If I took the H, that would mean that the remainder is just OCli. I basically just chop off the H. And to be extra clear here, I'm going to label the element that we took along the edge here in yellow. Again, to reiterate, what I did here was match up the element of H to give me the remainder of my subproblem, which is just OCli in blue. And what I also want to be sure to do is take all possible choices here. So I just took H. I could also take an HO because HO also matches directly at the very start of my input string, right? So if you took an HO, then your remainder is just CLI, right? So this is really critical logic for this problem. And notice how things are structured, right? From this node of HOCLI, if I match up the H, then I just have OCLI. But if you're back at the top, if you took the HO, then you just have CLI. That's how I'm breaking my subproblem down further and further. If I wanted to describe this step in words to an interviewer, I would call it matching a prefix. The word match here refers to the fact that we're checking if some characters are equivalent. And prefix refers to the fact that we're checking the equivalence at the very start of our target compound, right? I was looking at the H and then the HO. Checking for a match along a prefix is really important because it helps us stay organized. I'm always looking at the same spot within my target compound. All right, so let's keep it rolling here. Doing a quick sanity check, I feel really good about this strategy so far because it shrunk my problem size, right? Notice that at the root of my recursion tree, I had 5 characters originally. And going down this left-hand path, I have 4 characters remaining, right? And it even got smaller on the right-hand path. I only have 3 characters remaining. Because like we said before, in our intuition, if we reduce the problem size, eventually we're going to be able to solve the problem because our problem is going to get trivially small. So let's keep applying this same pattern. I'm going to look at this node on the left-hand side, OCLI, and I apply the same strategy. I look for a matching element in a prefix of my input here. So I look at the O, right? O is an element that matches directly. If I take the O, then I'm just remaining with a CLI. There's actually no other option you can take. Your only choice here is the O. So we'll break it down further for the CLI. In this particular case, there are 2 matches you can take at the prefix. You can take the C or the CL. And the important thing here is I'm going to explore both, right? For now, let's explore both. So if I take the C, then I just have an LI remaining. If you take the CL, then you have just an I remaining. It's important that we take both possible options, or in any case, all possible options, because you can't be certain which one is going to lead to the correct result. So you should be exploring every possibility, right? At this point, I can break things down further. If I look at this LI, I check for a matching prefix. It happens to be the case that I can match the entire thing, right? I have an element LI. So if I match up LI, I'm still going to label LI along the edge in yellow, but because that is my entire string, that gives me a remainder that's just the empty string, right? So this empty white box here just symbolizes the empty string. We'll talk more about that in a moment. Let's go ahead and flesh out this node I over here. I really apply the same rules, right? So I need to match a prefix here. Luckily, I can match up the entire thing because there's an element I in my options. If I do that, I get another empty string as my remainder. Hopping all the way to the top right for the CLI, let's break down this one further. Here's a case where I have 2 matches. You can either match the prefix of C or CL, so you're going to go down both paths. And you would continue this process for all of the children. I think you get the idea now. So we just hit an important part of the logic here, right? We broke down our problem further and further until we got to the empty string, which is great because the empty string is really the smallest string we can have, right? There are no characters in the empty string. And what's great is you notice that I ended up at the empty string in 4 different ways. You can see there are 4 paths that terminate in the empty string. Let's say I look at this left-hand most path, right? If you look at the characters in yellow, those would be all of the characters we took that actually build up to our initial string of HOCLI. In other words, if you do H plus O plus C plus LI, that is one way that you can get Hockley, right? And there are a few other ways to do that. There's also this path over here, and it's slightly different, right? Notice that it still starts with an H and also an O, but then it differs at the CL, right, into the I. Now, I'd give you another way that you could generate Hockley. And the same is true for other paths here. I'll just throw them up on the screen, right? You can do HO plus C plus LI. And finally, you could have done HO plus CL plus I. Those are the 4 different ways you can generate Hockley. These empty strings are really critical to the logic of this problem because they describe the base case, right? If you have the empty string, then what you should do here is return true. What you're logically saying is, if someone asked you to generate an empty compound, well, that's always possible. You should return true. To generate the empty compound, just do nothing, right? You don't even have to add up any elements because you're asking for the empty compound. Remember that this tree is symbolizing the recursion for this problem. So that means that every node represents a particular call to the problem. These empty nodes at the bottom represent the base case call. What I'm saying is they're all going to return true because it's always possible to create the empty compound. So that's going to be the base case that we're eventually going to translate into some code. And you probably already have a sense for the recursive step. The recursive step is how we broke down our problem size smaller and smaller as we built this tree. If I wanted to describe it in words, I would say the recursive step here is to reduce the string by matching a prefix. Obviously, this is going to require some particular method calls when it comes to our code implementation. That's overall the logic we're trying to accomplish. We're being sure to reduce the string, because if I reduce the string, it's going to work toward the base case until I hit the empty string. Let's highlight something tactical that we've been doing so far in this planning phase. It's what the best candidates do. If you also do this on your tech interviews, then you'll really stand out as a strong candidate. We already spoke about how important it is to label what type of problem you're given. As you describe your conceptual solution to the problem, you should continue this style of communication by using keywords and key phrases. What do I mean by keywords? We're using specific terminology here. Words like recursion, base case, and recursive step. We also use the key phrase like match a prefix. This statement is really important because it will directly translate into the code. The phrase match a prefix actually captures a lot of the logic that we'll need to implement later on. Not only does it imply that we'll check if some string characters are equal, but because we said prefix, this means that we'll do the check at the front of the string. Prefix is also a nice programmer word that your interviewer is going to be familiar with. They'll know exactly what you're referring to. We want to communicate with our interviewer in a clear way that shows our knowledge. Like we said with labeling, using keywords will also give the interviewer clear signals. They can either confirm that our strategy is good or disagree and push us to pursue another route. However, you can only receive this on-the-fly feedback if you're specific. For example, if you say recursion, but there is no recursive solution to this problem, then your interviewer is probably going to push back with some counterpoints and examples until you realize the flaw in the strategy. Like before, don't view receiving hints toward the right direction as failures during the interview. It's not a failure. The interviewer is just trying to get you on the right track. By using keywords early on, you can avoid blindly committing to an incorrect strategy. It's better to change direction now while it's early in the planning phase, rather than after you wrote a ton of code. With that in mind, let's trace through another test case. Here I have the compound cog, and I'll make this one much shorter. Let's say our elements were just C, O, CO, and OG. For this particular input, the final result should be a true. And one way you can see that here is to just do the simple C plus OG. That would most certainly spell out cog. But let's follow the same recursion tree logic for the smaller example. So I'm going to start with my top level problem, just COG, and I follow the same logic as before. So I'm looking for a matching prefix using my elements as options. So I could take the C, right? If you took the C, then your remaining compound is just OG. But you could have also took the CO. If you took the CO, then your remaining compound would have been just G, right? I'm always exploring all possibilities. Great. From here, let's flesh out the OG. So from here, you could take just the O or the OG. If you take the O, your remainder is G. If you take the OG, you end at the empty string. Great. Let's keep going. If you look at this G node over here, here's actually a very important example. It's one where we hit a dead end, right? So I'm going to try to match a prefix using this G, but there is no choice of element that matches up here, right? If you look throughout, the only thing I have is really an OG, but that can't match up because I have nothing for the O. So for this particular example, this input, it should return false. G is a dead end. It's not possible to create the compound G. And that would also be true for the G on the right-hand side here, right? For the input G, it's not possible to create that compound. So those are two function calls that should return false. And like we said before, looking at this empty call over here, that's just the empty string. It's always possible to generate the empty compound. So that's going to return true. So this recursion tree for cog represents all the possibilities we explored to generate cog, right? You can try to take a C plus an O, looking at the characters in yellow, but then you hit a dead end, right? C plus O, and you have nothing to take afterwards. So that doesn't work out. In a similar way, you can take the CO at the start, but you also hit a dead end, right? So that doesn't work out either. The only way that works out is if you take the C and then the OG, like so. And that would be the final answer here, right? And for this particular input of cog, you should ultimately return true, right? So why am I showing you this example that has a true possibility and also some false possibilities? Well, it's because we need to code up this logic later on. So how can you actually mediate these return values? Because I'm saying that the falses and trues are return values in your recursive function. Let's take a look at this node over here, right? This node is OG, and what it's trying to do is decide, is it possible to create the compound OG? Well, I know from the two children, it gets two different subresults. It gets a false and then also a true. Because it has at least one true, it should ultimately return true. It is possible to create OG, right? And this logic follows further. On this right-hand side, I know that this G is going to return false upward to its parent. So when I'm at the cog, at the tippy top, cog is going to get back a true from its left and also a false from its right. Because it just needs one true to be possible, it's going to return the true. So that's a logic we need to encode within our recursive function. If one of your child calls return true, then you should definitely return true. On the flip side, if all of your child calls return false, then only then can you return false. That's going to be some logic that we need to encode in our implementation. At this point of the interview, we've come up with a decent strategy, but note that we haven't written any code yet. We're still in the planning phase, and that's totally okay. Some candidates feel pressured to jump right into the code without discussing a solid plan. This is a mistake. Trust me when I say it, if you begin writing code without a concrete plan first, then you will only confuse yourself and the interviewer. If you have no idea where you're going, then I guarantee your interviewer certainly won't either. When this happens, the interviewer won't be able to get you back on track. Like we said before, the key to these tech interviews is to stay on the same page as your interviewer at all times. Explaining the logic both visually and verbally like we did is how we stay on the same page as the interviewer. If you drew this recursion tree and explained it to your interviewer, then they would fully understand your intent and be convinced that you really know your stuff. If the interview is in person, then sketching a diagram like this is pretty straightforward with a whiteboard or pen and paper. However, if you're interviewing remotely, things are a little more challenging. What I like to do is create a text art version of the diagram. It looks difficult, but if you actually practice doing this at home, you'll be comfortable creating the text art on the interview. So what's next? We sketched out these recursion tree diagrams, so we're fairly confident that our algorithm will be correct when we code it up. However, being correct is only half the battle. Yeah, your algorithm will be scored based on correctness, but also efficiency. Correctness is whether or not the algorithm returns the right output. On the other hand, efficiency is how much time and space the algorithm consumes. Like you might have heard, we use big O notation to determine the efficiency. My pro tip for you is to start a dialogue about big O early. Many candidates will only discuss big O after they write all of the code. I think this is a mistake. Since we formulated a concrete plan on the whiteboard, we should be able to at least provide a rough estimate of what the complexity is before we write any code. Now, don't worry, you don't need to predict the exact big O complexity. The exact big O will depend on the code. Right now, we just want an approximate categorization. What I mean is, estimate if your algorithm is linear, quadratic, exponential, etc. It's beneficial to provide an estimate early because your interviewer will have a big O efficiency goal in mind. If your planned algorithm does not meet their efficiency goal, then they'll likely nudge you to either modify your strategy or choose a new one completely so you can hit their target. Again, we're trying to use our interviewer to our advantage. Most interviewers are good people and want to see you do well, so you need to maximize their guidance. Anyways, if your estimated big O is in line with the efficiency goal that they have in their mind, then they'll likely give you the green light, thumbs up, and push you to start writing the code. This will give you a huge vote of confidence because you know that you're right on the money. With all this being said, let's head back to the whiteboard so I can show you how to estimate the big O for our chemical problem. Whenever it comes to describing the time complexity, I think it really helps to think about the worst case example, because the time complexity should describe the performance of our algorithm as our input gets very, very large, right? Large things generally are our worst case scenario. And so I'm going to focus on the time complexity here because really that's the important aspect of this particular problem. So what I'll do is I'll give myself the compound that consists of just a bunch of O's, right? It's kind of trivial in that it just repeats the same character again and again, but it's pretty long. Let me say that my elements are going to be some other O's. I can either have a single O element or a double O element or a triple O element. You can probably already see why I chose this particular example. It does give me a little bit of like a worst case scenario, meaning that there are many options that I can take, and I have a very long string. To keep my notation simple, it's going to be kind of hard to see all of these O's on the screen at the same time. I'm going to abbreviate things here just for the purpose of our diagram, right? So I have my 12 O's as my compound, and for the elements, I'll abbreviate them as 1O, 2O, or 3O. Remember that for the compound, when I write like literally 12O, I just mean a string consisting of 12 O's. So let's do the breakdown in the same way as before. So at my top level problem, I have 12 consecutive O's. And like before, what I need to do is match a prefix using my elements. And so you can match really all your prefixes here. You can do a 1O match at the start, in which case you have 11 O's remaining, right? I'm really just removing that 1O that I matched up. In a similar way, you could have also went along the 2O match, in which case you have only 10 O's remaining. And of course, you could do the 3O match at the prefix, in which case you only have 9 O's remaining. So nothing too fancy here. I'm doing the same matching a prefix logic as before. I just have different notation to kind of squish these O's down, right? I continue this process further. Looking at the 11O in blue over here, that would branch off like this. Again, I'm always just going to branch off using my 1O choice, my 2O choice, and also my 3O choice. This process goes further and further. You kind of get the idea here. It gets really repetitive. You can probably have some intuition here that the tree for this gets very, very large. But let's notice a pattern within this tree. You don't need to draw it out fully, and I most certainly wouldn't draw it out fully in my interview, but draw just enough of it so you get some intuition about the shape of it and the pattern, right? So what I would do is first notice how many nodes do I have going across each level. So what I mean is I can start at the top of my tree here. And when I say level, what I mean is all the nodes going across here. So at the root, of course, there's only just one node, right? On the next level going downward, that would be 3 O's, right? Because I branched off for each of my 3 elements. But on the next level, I would have 9 nodes. And then if I actually drew it out, on the level below that, I would have 27 nodes. And this pattern would continue further and further until I hit the very bottom. But I think we could already start to see the pattern. You'll probably notice that from one level to the next, you'll notice that I triple the number of nodes. In other words, at the very top, so if you want to like generalize this pattern mathematically, at the very root, you definitely have only one node. And then you triple it to get 3 nodes on this level. You triple it again to get 9 nodes here. And then triple it again to get 27 nodes here. And this pattern continues. I'm really just multiplying by 3 for every level within this tree. And that's an important aspect we can use to start describing the relationship for the big O, time complexity. And so I know that I'm going to be doing a lot of times 3 here, right? Because that would tell me the number of nodes in this tree, which is really the number of calls in my recursion. So I guess really the question is, how many times do you triple things, right? How many times do you do this multiplication by 3? What you can do is try to notice a structure here. And so looking at our very top level input, we have 12 O's, right? As our top level problem. And in the worst case scenario, what we'll do is take a bunch of baby steps, right? Maybe we only match the single O's. So in other words, going along this left-hand path here, I have 12O, then 11O, then 10O, then 9O. And if I kept going down this leftmost path, I would just go by ones, right? It would go 9, 8, 7, 6, and so on until I hit the empty string, which is really just 0 O's. So what does that tell me? Well, that's really just a countdown, right? It goes 12, 11, 10, 9, all the way down to 0. So that means that the total height of this tree, we can say is like about 12. It's roughly 12. So that means I have to multiply 3 by itself 12 times, right? That would give me the total number of nodes in this tree, which is really the total number of calls during your recursion, right? It's 3 to the 12th power. But I do want to generalize things over here. So here I had this hard quantity of initially 12 O's, but I want to generalize things. So looking at my 2 inputs, let me start by describing them using some terms. So I'll say that C is going to be the length of my target compound. I'll also say that E is going to be the number of elements. Notice that here I'm using a different variable term for each of my different inputs, right? That's pretty intuitive. And now I want to generalize the math here on the right-hand side. So instead of times 3, right, we may not always have 3 elements. In any case, we could have a variable number of elements. So I'm going to replace the 3 here with just an E, right? You would branch off at every level based on the number of elements you have as options. And in a similar way, I need to generalize this 12, right? This 12 really corresponded to the length of my target compound. So I would replace that with a C. All right, so now I have things nice and generalized, right? If C is the length of my compound and E is the number of elements, the total nodes that need to be explored in this recursion tree would be E to the C power. Notice how it matches the hard quantity on the left-hand side. And that means our total time complexity for this one is exponential. It's exponential because the variable C is in the exponent. Exponential is typically considered a slow complexity, so we have some work to do here. At this point, we've identified that our initial strategy will have an exponential time complexity. Unfortunately, exponential is quite slow. Your interviewer would certainly want something faster. For many interview candidates, this is their worst nightmare. We just spent a lot of time exploring a strategy, and it turns out that the strategy we chose does not meet the big O expectations of the interviewer. This is exactly the situation I found myself on the Google interview. But I was still confident. I was confident because I knew I had the interviewer exactly where I wanted them. That's because I knew exactly how to improve the performance. I knew I didn't have to abandon the entire strategy. I only needed to adjust it with an optimization technique. This is where your experience comes into play. Going into the interview, I had practiced this type of problem a lot. But to be honest, if you haven't learned this technique before coming into your interview, then there's probably no chance that you'd be able to pass the problem. For the purpose of this video, I'll go slow and teach you the technique since you might not already be familiar with it. The first thing you'll want to know is that this optimization will build directly on top of the brute force exponential strategy that we just explained. This means that we should start coding up the brute force implementation. Coding up this particular brute force solution is not going to be a waste of time, and you'll see why in a moment. Let's head into my code editor. Here I am in my coding environment. I'll leave a link in the video description below where you can follow along. I'll be doing it in Python, although you can switch your language to JavaScript, C++, Java, or Python as well. But you should be able to follow along nonetheless. So here on the left-hand side, we do have the description of the problem like we spoke about already on the whiteboard, as well as some test cases. But we want to really jump into the code for this one. I think we're done laying out the strategy on the whiteboard. So what we'll do is we'll start by laying down that base case. Like we said, it's all about checking the length of the compound. We're going to treat the empty compound or the empty string as our trivial base case. So here I'll just check if the length of the compound is 0. If that's the case, then I'll just return true. In other words, I'm always going to treat it as if it's possible to create the empty compound, just like we said in the whiteboard. Now from here, I do want to iterate over my different elements. So I'm going to iterate for every element in elements. So the elements list is this long list for this example. On the first iteration, element would be NE. The next iteration, my element will be O. For each of these elements, I'm going to check if they match a prefix of my current compound. So luckily in Python, you have a nice helper method you can use. You can say compound dot starts with, check if the compound starts with this given element. And we'll actually do a quick little spot check here, make sure we're on the same page. Like you expect, you could have some string, I'll just say A, B, C, D, and I can do dot starts with, and here I'll check if it starts with A, B. This should obviously give back a true result. So I'll just print it out, hit our run here. Run is just going to execute this file as a script. I see the true. If I check if it starts with A, B, E, that should get back false. Nice. Do note that the starts with method, at least in Python, is going to be case sensitive. So we do have to do some adjusting here. Because I know based on the description of the problem, it looks like my compound itself is going to be all lowercase, but the elements are going to have a capital letter at the start. So I'll just be sure to also lowercase the elements over here. So now it'll just be a matter of doing dot lower in Python. So nothing too hard to actually fix that aspect of the problem. Do note that on your interview, sometimes they do annoying things like mess up the capitalization. So you should know how to reconcile that. Usually just make sure they match in their capitalization. So make sure both things are lowercase or both things are uppercase. So looking at my code here, I'm saying if the element matches a prefix of my compound. And if that's the case, I want to make a recursive call. So I'm going to call valid compound. And I need to pass in some smaller compound over here. I'm still going to pass in the original elements. In the problem, they tell us that we can reuse elements as many times as we need, so that's why I'm passing along the same exact elements. but I should pass in some smaller compound over here. Basically, I want to chop off the prefix I just matched. So for example, if this is my current compound, and my element is Ne, I can see that Ne matches the prefix over here. And so I want to take the CO and call recursively with it. So what I'll do here is I'll just do a little bit of a Python slice. So I'll just get my remaining compound, lose a variable, and I'll set it equal to the original compound, grab a little slice. I'm going to start slicing at the length of the element and go through the end. Great. So like I said, if this is my original compound, if I take the length of my element, that'll be 2. I'm going to start slicing at index 2. So I go 0, 1, 2. So I'll grab the CO and I pass that along recursively. So this kind of boils down to a CO here. Of course, I'll use the variable. Nice. Now I think about the results I get from this recursive call. I know this returns a Boolean, right? Should be a true or false. So I'm going to check. If I get back a true, then I could ultimately return true. Great. Now the question is, how should I return false? You don't just want to do else return false. Don't fall into that trap here, because you want to be able to check any possible elements that match a prefix. So if you write it this way, you're most certainly only going to do one iteration in code like this, because you have return true, else return false. The way you want to return false is if you finish iterating through all elements and you don't find a matching prefix. So I do a late return false after the for loop here. Great. And do try to think about how this code relates to that tree diagram that we sketched out on the whiteboard, right? The different branches that came out of any node correspond to this for loop, right? Making a recursive call on some matching prefixes. Great. And every node in that diagram does match some compound that we're calling recursively. This is actually all we need for the brute force solution of this one. Let's give this a test run. So we're passing most of our test cases. We are going to time out on, looks like test case 0.5. If I scroll down here, test case 0.5 is very large, right? And so we'll have to figure out a way to optimize this one. Hopefully now you're feeling good about the brute force implementation. We saw that it does return correct results. However, for very large test cases, it takes too long. This is consistent with the exponential runtime that we estimated earlier. Let's head back to the whiteboard and discuss how we can speed it up. So let's go back to a previous example and figure out how we could speed things up here. So we initially traced through this Hockley example, and we ended up building this recursion tree. And previously we already recognized that in terms of our big O notation, if you say that C is the length of our compound and E is the number of elements, then in general, the number of nodes in this tree would be E to the C power, which would also tell us the time complexity, right? Because you have to evaluate each of those recursive calls. That describes the brute force complexity of this solution. But let's start to notice a pattern within this particular tree. If I look at this subtree, highlighted in pink, notice that it has Li as its root node. And I can see this subtree somewhere else. It appears on the right-hand side right over here. And notice that it's identical. That's just something interesting to notice. But this pattern occurs in other places too. If I look at this subtree rooted in I, here I have it in navy color, it's also on the right-hand side over here. And again, it's identical. And this pattern carries up further. If I look at this CLI node over here, this entire subtree, so starting at this CLI node and going all the way down, it's totally duplicate on the right-hand side over here. So we just identified that some parts of this recursion tree are totally identical. That tells us that we have duplicate subproblems. And because I have duplicate subproblems, I should be able to optimize things here because it's a dynamic programming problem. So I'm going to use a dynamic programming strategy. The way I teach all my students to solve dynamic programming problems is to use memoization. So here's what we'll do. We're going to use an additional data structure. We'll call it our memo. And under the hood, when we go ahead and implement this in some code, you just want to use a hash map, right? So if you're in JavaScript, use an object. If you're in Python, you use a dictionary. If you're in Java, use a hash map. If you're in C++, you can use an unordered map. What you're looking for here is to choose a data structure like a hash map because it has an O of 1 lookup and O of 1 access. Great. So I'm going to show you how you could use this additional memo to speed things up over here. So when it comes to this recursion tree, the way it evaluates is in a depth first order, right? So really the first call that we'll evaluate will look like this. I initially try to call and finish Hockley, but I have to go down the left-hand side to Hockley and then CLI and then LI till eventually I hit my first base case, which is over here, right? Here I have the empty string as my input, which would be exactly one of our base cases. Here we can immediately return true. So this call is going to return true. It returns true to its parent. So return true to this li over here. Now this li call is going to return true. And so here I'm saying that the result for li is true. I'm going to save that information in my memo. So I'm going to add a key of li and make its corresponding value true. I'm going to save this subresult for later on in case I need it. And so this will carry up further. I want to evaluate this CLI on the left, but I still need to evaluate all of its children. So I go down to the I over here, and then down to the empty string, which of course is another base case. So this empty string is going to return true to its parent. That tells me that I has a subresult of true, and I want to add that information into my memo. That means I add a key of I, and I make its corresponding value true. So I save that subresult for later. Now I can finally evaluate at CLI. Because both of its children are true, CLI could ultimately return true. And again, I add the subresult into my memo. I take the corresponding subproblem, which is just the string in blue, which is CLI, and I make its corresponding value true, which is the subresult for that particular input. At this point, I can now evaluate at OCLI, and OCLI is going to return true because its one child is returning true. I need to be sure to add that into my memo though. Now I try to evaluate at my top level HOCLI, but I haven't yet evaluated in my right subtree. So I need to evaluate that first. And here's the really important part. I'm looking at the subproblem CLI, and what I'll notice is it's already within my memo on the right-hand side. It's right over here. And so I don't need to actually traverse and evaluate all of the children of this node because I already know what the ultimate answer is going to be. So instead of manually evaluating all of the children of CLI, I can just have it ultimately return whatever I have stored in the memo, which would be a true result. That's because I already calculated this entire CLI subtree on the left-hand side over here. And it would be totally duplicate on the right-hand side, so there's no point of redoing any of that work. So I can ignore all of the children over here, basically cutting them out of my tree, which would of course means I don't have to evaluate them recursively, which makes my code much, much faster. At this point, I'm ready to evaluate at my top level root, HOCLI. Both of the children are true, so I can ultimately return true over here. And of course, you would also technically save that into your memo. The point is, notice how much time we were able to save, how many recursive calls we were able to save by using this memo. In terms of our time complexity, we're able to optimize things here. Our original brute force was e to the c power. When you apply memoization in this way, you'll actually reduce that down to just an e times c. Notice the difference in these quantities, right? In one, I have an exponentiation, right? You're doing e to the c power. And on the right-hand side for memoization, we're just doing e times c. And that's actually a really large improvement. If you want some intuition on the difference between these quantities, just plug in some values. Let's say that we're doing e as 3 and c as 12. Well, then 3 to the 12th power would be over 500,000, right? But if you just did 3 times 12, that would be just 36. So notice how we're able to really cut down on the complexity for this one. And that would be a very acceptable, really the most optimal solution for a problem like this. We didn't talk about the space complexity yet though, and it's pretty straightforward here. If we talk about the space complexity, we have to pay attention to a few different things. For one, we did solve this one recursively, so we want to look at any space used from the call stack, right? Because every time we call a function, we add a stack frame onto the call stack. Using this type of diagram, the space consumed on the recursive call stack would just be the height of this tree. Like we said before, the height of this tree is just c, because in the worst case, you would just take single character matches along the left-hand side. In other words, you start with your string here, you match up an H, match up an O, match up a C, and here we match up technically an LI, which is 2 characters. But you can imagine in the worst case scenario, you would just take a bunch of single character matches. So that tells me due to the recursive call stack, my space complexity is at least O of C. Let me also use some additional space from our memo, right? We said that our memo would be like a hash map object. So we have to think about what are the number of entries that we'll put in this memo? Well, in the worst case scenario, it would just be every possible compound, right? Which would be based on C. So that'd give me another term of C. So you're really looking at a C plus C space complexity. Of course, you could simplify this down. 2C really just evaluates to C following our classic big O rules. So now let's optimize this. I do want to use that memoization strategy. What I love to do is give myself a main function. And this old recursive function is now going to be a helper. I'm going to give it an underscore in its name, just so I can have two different functions. So if I just wanted to make sure nothing breaks here, I'm going to have this main function, which is without the underscore. It's just going to call the recursive helper. So I'll pass in compound, also pass in elements. So if I give this a test run, I want to make sure this still works as much as it did before. So it's passing the test cases, except it's timing out on that very last one, which is the large test case. Cool. The reason I like to do this is now it gives me an opportunity to pass in an additional argument. I'm going to pass in an empty dictionary into my recursive function here. I'm going to take that in as an argument. Here, I'll call it my memo, just like we said in the approach. And here is where I need to add the memoization logic. So the first thing I need to do is check if I've seen this subproblem before. Recall that based on our tree diagram, the subproblem is like defined by what compound string we're given. In other words, I want to check if I've seen this compound before. So the way I can check that is check if the compound is in the memo. This will just return a Boolean telling me whether or not compound is a key of the memo dictionary, right? Dictionary is just a hash map in Python. And from here, if I've seen this compound before, then return the stored value. So return memo at compound. Cool. So I'm checking if the key is in the dictionary. If the key is there, then return the corresponding value. Great. Obviously, if we're going to do this operation, then we need a way to actually store information into our memo. And what I do is I look at my recursive function. I want to locate the recursive step, right? So this is the base case, right? Everything else is the recursive step. I look at the return values in the recursive step. There are really two return values here. There's a return true and also return false. And what I want to do is add those subresults into my memo before I return. So down here it says return true. What I would do is say memo at compound equals true. I'm saving this subresult in my memo for later on. A similar way I would do it over here. So memo at compound equals false. So I'm not changing anything logically here. I'm still doing the same return value. It's just that before I do that return value, I'm storing that subresult. Notice that the key I'm using for the subresult is the same as the argument that comes in. It's just the plain old compound. Great. The final thing I need to do is make sure I share this memo hash map to the entire recursion. So this recursive call here should also take in that argument memo. Do bear in mind that my recursive function is the one that starts with the underscore here. I did that so I can pass in an additional argument. Great. And this is going to be really nice because in Python, our dictionaries do have a constant time lookup and access. So these operations of checking for membership in a dictionary runs in constant time. Even adding things into the dictionary is also constant time. And like we said in the whiteboard, by doing it this way, you should be able to cut down on your complexity. Notice how now I'm passing that test case 05, which is indeed the large test case. And so there's our memoized solution. Notice that it is passing that large test case. There is another optimization you could do. What you'll notice is in our recursive function right now, we actually do an additional linear operation. So if I look at this expression, so this expression over here is going to run in linear time based on the size of our compound because it creates a copy of the compound, just removing the first few characters that matched up for the prefix. But if I wanted to optimize that away, I can show you a little trick to do that. So let's go ahead and avoid doing this slice operation. What you could do is not change that argument by passing in an index number. So I'm going to pass in 0 here. I'll pass it in here as well. I'll just call it IDX. So initially, IDX is going to be 0. Cool. So that means I no longer want to actually mutate the compound argument. Instead, I want to deal with the index variable. So I'm going to start to rewrite things over here. Let me start with this code, which was our original base case. So instead of checking if the compound is empty, now you have to check that logically using your index. What I would do is I would check if my index is equal to the length of the compound. So the important thing with this kind of trick is I'm no longer going to shrink the compound itself. Instead, I'm going to increase this index. You can think of this index as representing the logical start of the compound that I'm looking at. So initially, my index is set to 0. That means that I'm looking at the entire compound because I start at index 0 and go through the end. If currently, let's say index was 2, that would mean that I'm looking starting at the character at index 2 through the end in compound. To make sure we're on the same page about this index trick, let's go ahead and look at an example. Let's say that our compound string is ABCDEF. We know that the length of this string is 6, which means that its indices go from 0 through 5. The index argument that we're adding to our code is going to correspond to the starting point of the string I'm looking at. So if your index is 0, you're looking at A through F. If your index is 1, you're looking at B through F. If your index is 2, you're looking at C through F. Likewise, if your index is 4, you're looking at E through F. If your index is at the final index 5, then you're just looking at the very last character, F. Notice that the rule is the index is going to correspond to the starting point of the string. You're always going to start at that index character and go all the way through the end. And what we can do is also give ourselves one final step. If we say that we go out of bounds, so right now my index is pointing to 6, which is most certainly out of bounds of my string because the final index is 5. If ever your index is out of bounds, then you're going to be looking at the empty string, which is going to be really important because that was, of course, one of our base cases. Let's head back into my editor. So IDX is going to represent the logical start of the compound I'm considering. So that means if my index ever reaches the very end of my compound, that represents the empty compound, the empty string. Cool. And so I need to adjust some other places as well. Down in this logic, when I do starts with, I don't want to check if my compound starts with the element at the very beginning of the compound, because now I have the IDX representing the logical start, right? So what you could do is starts with takes in an additional argument. You can pass it in over here. That's going to be where you perform the search. So this is a little tricky, so I'll kind of break it down for you. So let's say that your compound is this string. We'll say A, B, C, D, E, F. And I did dot starts with. And I'm going to do starts with, we'll say, C, D. This will obviously return false. We'll print it out. I'll be sure to hit run, just run this code below. So I get back false, right? Because CD is definitely not found at the beginning of the string. But instead, what I could also do is pass in this additional argument and check the starting point. So I'm going to check out that starting point 2. So counting my indices, it goes 0, 1, 2. 2 would be the index of the C. So now if I run this, this will go back true. So that's the logic we're using here. So I'll comment that out. So this should adjust accordingly. And now when I grab my remaining compound, we no longer want to actually perform the slice. That was the whole point. So I can avoid this linear time operation. Instead, I want to use the original compound and just figure out a smart way to manipulate the index. Right? I do want to increase the index because eventually my base case needs it to actually hit the very end of my compound. What I can do is increment the index by the length of the element that I chose. So for example, if my element, let's say, is NE, when I take the length of it, it's 2, I'm just adding 2 to my index. So if it is 0 right now my index is going to be 2. And that keeps me progressing toward my base case. Right? I'm just kind of reframing all of these string slicing logic into this like index analogy. Great. But I do need to adjust the other parts of our code. It's no longer the case that the compound is changing through the recursion. That was the point to make it faster. So I need to change the keys into my memo. Instead of the compound, you want to use the index. Your rule of thumb is just always use the argument that changes during the recursion. The argument that changes is the index now. It kind of describes which subproblem I'm at. So I'll change that to IDX. And likewise, when I access the memo, I'll do that based on my IDX. So logically, this shouldn't change any meaning in our code, but we are able to avoid that linear slice operation. So I'll give that a test run. Great, and there we have it. And that wraps up the interview problem. I hope you found this video useful, especially if you're preparing for algorithm interviews. I went through the long Google interview process myself, so I know how intimidating it can be. If you want to know the complete study strategy that I used to land my job at Google, then click or tap on the screen. I'm Alvin, and I'm obsessed with teaching people data structures and algorithms. If you want to hear more tips from me in the future, then hit subscribe and I'll see you next time.